Good afternoon, everyone. So let us wait for 5 more minutes since this is the first session for others to join. Uh, and we'll start the session in 5 minutes. So, and yeah, we can just I'll introduce the course and myself in the meantime. So this course is NPTEL course, Fluid and Particle Mechanics. The course code is NOC 25CH49, and this is course instructors are Professor Sumesh P. Thampi and Professor Basavaraj M. Gurappa from the Department of Chemical Engineering, IIT Madras. And these are the live sessions wherein we solve problems that will help you in submitting the assignments. So since as you all know, this is for helping you in solving the problems. So which will again in turn help you in submitting the assignments. So and this is myself Ainkara. I am a research scholar from the Department of Chemical Engineering, IIT Hyderabad. So I'll be handling these sessions wherein we solve problems related to that week's session. I mean that week's assignment. So which will help you in submitting that assignments. Yeah, yeah. We'll start at 3:05 exactly. So, since today's session is the first session, we will just see an introduction to the course layout and books and references given in the course. Followed by, we will see problems related to week 1. So, if at any point of time you have any doubts, you can stop me and ask. And these sessions are being recorded, which will be made available to you as well. So yeah, if you have any suggestions for me to go fast or go slow or anything else, you can stop me at any time and you can ask. You can tell those as well. And yeah, if you have any answers, you can discuss those as well. So this is just like an interactive sessions, which will be helping you guys to solve the problems related to that specific week. So if someone wants to say anything, you can say like in case you have any expectations on the on this sessions, you can always tell. All right, we'll start. First few slides are anyway some introduction only. So yeah. This course, as you all know, it is a 12 weeks course. So mostly, as the name suggests, it is fluid and particle mechanics. So most of the chemical engineering, I hope most of you are from chemical engineering background. And as we all know, most of the processes we encounter, we either deal with fluid or we either deal with solids in most cases. And also the particle mechanics, which we are talking about, if we go to industries, it is very much required to know about particle mechanics, because most of the process you will have you will be encountering particles in either raw materials or in products. In any form there will be uh, requirement to deal with the particles, and dealing with particles is not an easy task, because it is very much difficult to ensure that the particles are behaving as you expect. So to understand all those, you must have a very thorough knowledge on how the particles behave. There are various factors which which influence how the particles behave inside the system. So this course, as the name suggests, it is about fluid and the particle mechanics. So as the course goes, you will be having an idea on how these things are going. So the first thing when we talk about fluid mechanics, as we all know, it is about mostly we need to understand how the fluid is uh, behaving inside the system, how it is going, how it is flowing. So we need to understand basically the flow mechanisms, and we for that we need to know what are all the equations that are governing the fluid flow. So when we talk about equations governing fluid flow, the first thing that comes to our mind is Navier-Stokes equation. So because whenever we are talking about pure fluid flow like cold flow, there is no energy involved, and there is external heat, those type of things, and there is no mass transfer involved as well. Mass transfer or phase change or any chemical reactions, if all these are not involved, we solve only for continuity equation and momentum conservation equations. So for that we need to know how these equations and what are all the terms in these equations. So the first week 1, it is about introduction to Navier-Stokes equations and their exact solutions and partially flow. And week 2, it is about Taylor-Couette flow and rheology. And week 3, it is dimensional analysis. And week 4, it is turbulent flow. And week 5, it is friction losses, Moody chart. And week 6, it is boundary layer theory. And week 7, introduction to particles, characterization. And like mostly it is about first few weeks you will be seeing about fluid mechanics, and followed by you will be having about particle mechanics. So week 8, it is particulate phenomena, Brownian motion and forces. Week 9, motion of particles in a fluid, terminal velocity, particle separation. Week 10, it is sedimentation of dilute, concentrated, flocculated dispersions. And 11, it is packed and fluidized beds, and week 12, it is filtration. So myself, actually I am working on fluidized beds, which comprises both fluid and the particles. So we all know that systems behave very complex under different conditions. So to if we have a thorough understanding of how these basic behavior of particles inside the system are, we will be able to control the things in the future. So now as for the books and references, we have a few. Just a minute. Yeah. So first one is Unit Operations of Chemical Engineering, McCabe and Smith. And so this we all have studied. We mostly will be using it as a reference for all the chemical engineering subjects. And second one, it is Fluid Mechanics by Frank M. White. And third one, Introduction to Particle Technology, Martin Rhodes, John Wiley and Sons. And for references, we have few: Coulson and Richardson's Chemical Engineering, and Fluid Mechanics, Piyush K. Kundu, Elsevier 2013, and Principles of Colloid and Surface Chemistry, Paul C. Hemans and Rajagopalan. So last one is transport phenomena by bird, Stewart Lightfoot. So yeah, so now we will move to problems. So if you have any suggestions during the problems, or if you have any doubts, you can always stop me and ask your questions. So first question it is, constant thickness film of viscous liquid flows in laminar motion down a plate inclined at an angle theta as shown in figure. The velocity profile is u is equal to cy into 2h minus y. I mean u profile is given in terms of y, and v and w velocity are 0. So what is happening? A constant thickness film of viscous liquid flows in laminar motion down a plate. So here fluid of constant thickness is moving down a plate which is inclined at an angle theta. So this velocity profile is given by u is equal to, u velocity component is given by c into y into 2h minus y, and v and w components of the velocity are 0. So here c is the constant and which is unknown, and y here it is the direction. So u velocity is varying with respect to y, as we all can see from the figure as well, and it is a function of h. H is the thickness of the viscous liquid film. So now what is being asked in this question is that find the constant c in terms of specific weight and viscosity and the angle theta. So we are asked to find what is c, and c here is given that it is given over here that c is a function of specific weight, viscosity and angle theta. So c is a function of rho, mu and theta. So we need to find what exactly is the c being denoted over here. So first let us see what are all the options given over here, and after that we will see how to solve the problem. So first option is option A, it is rho g sine theta by 2 mu. Second one, it is rho mu sine theta by 2g. Option C, it is rho g cos theta by 2 mu. And option D, it is 2 mu sine theta by rho g. And option E, it is rho g by sine theta into 2 mu. And we have the answer as option A, that is rho g sine theta by 2 mu. So now we will see how to how we got C value as rho g sine theta by 2 mu. So again, like since this whole week it is about mostly dealing with Navier-Stokes equations. So we will be using that and getting the solution only. So first let us see and analyze the figure. So first, when we are looking at the figure, what we are predominantly seeing is that here there is a flow of a viscous liquid. So mu is playing an important role. So c is a function of mu, which is also mentioned in the question itself. And here flow is laminar motion, and the plate, this particular plate is making an angle theta, and gravity is in this direction, and we have x and y is in these two directions. So here the u velocity is varying with respect to y position. So and v and w component of the velocity are 0. So this is the basic analysis from the figure. So now we will see the solution first. So when we are going with the solution, first we will write what are all the things given in the question. So what is given? A constant thickness film of viscous liquid flows in laminar motion down a plate inclined at an angle theta. So here we are having few things which we can take away from this statement. So first one is the thickness is constant, which is given as h, and viscous liquid, so it is mu, and laminar motion, and the plate is inclined at an angle theta. So velocity profile is u is equal to c into y into 2h minus y. So here u is a function of y, and v and w components are 0. So now what we are asked to find? We are asked to find the constant C, and that C is a function of specific weight, viscosity and angle theta. So these are all the things given and what we are expected to find from the question. So first, when we go about the solution, first we need to use the equations and only then we will be getting the solution. So first, let us use the continuity equation and see whether it is being verified or not. So when we are talking about fluid flow, like we know that continuity equation will be solved and it will be like it will be 0. So here it is an incompressible fluid. So here we are taking it like this. Dou u by dou x plus dou v by dou y plus dou w by dou z equal to 0. So here u is a function of y. So dou u by dou x is 0. Again v and w are 0. So dou u by dou x is 0 because u is a function of y, and when we are taking the derivative with respect to x, it becomes 0. And v component of the velocity and w component of the velocities are already 0. So this equation becomes 0, and since RHS is already 0, so we are able to say that continuity equation is being proved. So now next we need to solve for the Navier-Stokes equation. So Navier-Stokes equation, what it is saying, the generalized equation is that for in the x direction. So rho, because the flow is happening in the x direction, we are considering about the x direction. So rho into du by dt equal to minus dou p by dou x plus mu into dou square u by dou x square plus dou square u by dou y square plus dou square u by dou z square plus rho gx. So this is the Navier-Stokes equation in the x direction. So as we all know, we have x, y and z direction based equations. So here the flow is happening in the x direction, and so we are taking it with respect to x direction. Also v and w are already 0. So so since I hope till here we all are clear, and now we will substitute it everything in the equation and cancel out the terms, and then on doing so we will be able to arrive at the answer what is C. So now let us make some assumptions, and first one, it is a steady state, and so in the Navier-Stokes equations we have a pressure gradient term. In the question it is mentioned that a thin flow and flow is in the x direction. So for the thin flow, pressure along the x direction is not so varying, so pressure gradient is not there, like there is no pressure gradient which is driving the fluid flow, so we can consider that as 0 as well. So okay, so here u is equal to c into y into 2h minus y. This is what is given in the question, and if we multiply cy into all the individual terms, what we will be getting? We will be getting 2 into c into h into y, 2chy minus cy square. Just we are taking the cy inside the bracket and we will be getting it as 2chy minus cy square. So now what we are saying that u is a function of y, that we already saw in the last slide, I mean while solving for the continuity equation, but now we are very clear that u is a function of y. So now we are verifying the continuity equation. So we are just substituting it and we will be seeing it. Dou u by dou x plus dou v by dou y plus dou w by dou z equal to 0. So as we all know that u is a function of y, so this derivative becomes 0, and so this derivative becomes 0, and v and w are already 0. So this whole term becomes 0. So we are able to verify the continuity equation. So the next one is, we are now moving to the Navier-Stokes equation. So it is rho into du by dt equal to minus dou p by dou x plus mu into dou square u by dou x square plus dou square u by dou y square plus dou square u by dou z square plus rho gx. So what are we having? We are pressure gradient, we have seen it becoming 0. So we have the rest all the terms. So now what we will be having is u is a function of okay, yeah. So u is a function of y. So what we can say, we have three terms here, dou square u by dou x square. That becomes 0 because u is not a function of x. So u is not varying with respect to x. So dou square u by dou x square will be 0. Second term what we have, yeah, we have dou square u by dou y square. So dou square u by dou y square. How we can write? Dou by dou y of dou u by dou y. So this is the thing, dou square u by dou y square is equal to dou by dou y of dou u by dou y. So dou u by dou y, what we will be getting, if we take derivative of u with respect to y, we will be having 2 into ch minus 2 into cy. So now this is dou u by dou y. This is dou u by dou y. Now for getting dou square u by dou y square, we need to take one more derivative. So this term becomes 0 then, and this becomes minus 2c. That is how we got dou square u by dou y square is equal to minus 2c. So now we have gx. So here we are having gx. So here it is theta. Now we need to resolve the vector, and so this will be gx. Here it will be gx, and this will be like gy. Sorry, not in this direction. I mean, not in the upper direction. You're just getting my point, right? So it is gx we need to get. So gx is nothing but g into sine theta. So g into sine theta, when we resolve, we will be getting gx. So that gx we will be substituting back in the original equation. So now what we will be having, so the left hand side becomes 0, and I mean this whole term on expansion also you will be getting the 0, and equal to, this is 0, mu into minus 2c plus rho g sine theta. So mu, this term goes the other side. I'll clear the space. Yeah. So mu into 2c equal to rho g sine theta, because mu into minus 2c went to the other side. So we will be getting mu into 2c equal to rho g sine theta, and c is equal to rho g sine theta by 2 mu. So c is equal to rho g sine theta by 2 mu. So this is how we will be getting the answer. So c is equal to rho g sine theta by 2 mu is the answer. So I hope the problem is clear. So what was asked in the question, we were given a fluid flow and we were asked to find C. So we are told that a constant thickness film is flowing in a laminar motion down a plate. The plate is at an angle theta. So velocity profile, we are given u component velocity, which is a function of c and y, and v and w components are 0. So now we are asked to find c, constant c. So what we did for that, we first did the continuity and momentum conservation equations only we verified. So first we verified the continuity equation, later we moved on to momentum conservation equation, that too in the x direction. So we wrote the x direction equation and we saw that it is like a steady state and pressure gradient is not a major driving force because it is a very thin film, and and also it is a viscous force dominant flow. So we removed all those terms and we are left with these two terms, that is mu into whole term plus rho gx. So here we take the derivative of u with respect to y. We took two derivatives because it is a second order, and finally we got this particular term, which leads us to the final answer that c is equal to rho g sine theta by 2 mu. Okay, all right. Yeah. Okay. We can again discuss at the end also, like if you have any questions or anything, or if you want to have any discussion now also, it is fine. You can stop and ask. But yeah, so anyway, now we will go to second question. So in question 2, what we have in figure 1, if the in figure 1, if the fluid water at 20 degree and the width between plates is 25 mm, what shear stress in Pascal is required to move the upper plate at 7.5 meter per second? So what is asked in the question in the figure, if the fluid water at 20 degrees Celsius, I mean it is Celsius actually. Yeah. In figure 1, if the fluid water at 20 degrees Celsius and the width between plates is 25 mm, what shear stress in Pascal is required to move the upper plate at 7.5 meter per second? So what is given again, if we talk about this figure, fluid is water, and what is given, viscous flow induced by relative motion between two parallel plates. So we have two parallel plates. The bottom plate is a fixed plate and the top plate is moving at a velocity u is equal to v. So here again, if we look at it, we are able to see that this is y direction and this is x direction. So velocity u is varying with respect to the height, and the fluid is given as water. So viscous flow induced by relative motion between two parallel plates. So the plates are parallel plate and the top plate is moving at a certain velocity, and here the profile is in such a way that it is a function of height. So in the question, what is asked, what is given first, let us see. So the width between two plates is given as 25 mm, and upper plate is moving at 7.5 meter per second, and what shear stress in Pascal is required to move the upper plate at 7.5 meter per second. So we are asked to find the shear stress in Pascal. So first we'll write given. So fluid is water, that is one thing. Second one, width between the plates is 25 mm. The dy is equal to 25 mm. Second, velocity of the moving upper plate is 7.5 meter per second. And we are asked to find shear stress. So what formula we will be using? We will be using tau is equal to mu into du by dy. So now for solution, we will be just substituting everything, because we know du we know dy. So du is 7.5 meter per second and dy is 25 mm, and mu, here the fluid is given as water at 20 degrees Celsius. So for water at 20 degrees Celsius, the viscosity we can take it as 1 into 10 power minus 3 Pascal second. So viscosity of water, it varies between 0.0008 and 0.001. So based on the temperature, you can take the viscosity of water, or in general you can take the viscosity of water as 0.001 Pascal second. So now we know everything. Tau is equal to mu into du by dy. So du we know, dy we know, and mu also we know. So now since we know all the three things which we require to find the shear stress, we will substitute everything back into the equation. So we will get tau equal to 1 into 10 power minus 3 into 7.5 divided by dy is 25 mm. So we are converting it into meters. So whenever you are solving any problems, make sure the units are consistent. If not, it will lead to major errors. So it might look like a small thing, but it will affect the solution in a large way. So we are converting mm into meter. So we are multiplying it by 10 power minus 3. So now we are substituting everything. 1 into 10 power minus 3 into 7.5 divided by 25. So 10 power minus 3 and 10 power minus 3 gets cancelled. So this will be like 25 1 and this will be 0.3. Something is missing. It should be 0.3. Just a minute. Ten power minus 3. 5 yeah, I'll check later, but yeah, you got the concept right. So basically it is working based on that only. Mm, yeah. So now we will go to next question. What is the Reynolds number if L is taken to be the distance between plates? So what is asked? What is the Reynolds number if L is taken to be the distance between plates? So now L is the distance between the plates is given as if L is taken as the distance between the plates, and we are asked to find the Reynolds number. So Reynolds number is given as rho V rho into V into characteristic length divided by mu. So when we are going with the pipe flow, we will take it as D, and when we are considering particle dynamics, we will take it as particle Reynolds number, and that time the characteristic length will be dp, that is diameter of the particle. But in other if cases like this, it was here it is given as distance between the plates. So width between the plates is given as 25 mm, and velocity of the moving plate is given as 7.5 meter per second. So now we have to find the Reynolds number. So what is the formula for Reynolds number? Reynolds number is given by rho into V into characteristic length by mu. So here rho V L by mu. So rho is the density of fluid, V is the velocity with which it is moving, and L is the characteristic length, that is here it is the distance between plates, and mu is the viscosity of the fluid. So we are substituting all the known things in this equation, and we are getting it as rho is 1000 into 7.5 into 25 into 10 power minus 3 divided by 1 into 10 power minus 3. So here it is, if you substitute everything, we will be getting 1,87,500, which is the Reynolds number over here. So that is how the calculation is done. Now we will go to question 4. So before moving to question 4, what we have here is some kind of manometer kind of setup. So here we have 3 liquid system in figure 2. So this is figure 2. So we have 3 liquid systems. So here water, light pink color is water, dark pink color is mercury, and here oil is having specific gravity as 0.78. And light pink is water, medium pink is mercury, and dark pink one is oil. So we have 3 liquid systems. So we are having based on that, we are having different height being shown. So water is having 27 centimeter, and here oil is having some H2 height, and here water is mercury is having height H1. Here it is at height 8 centimeter. Here it is at 5 centimeter. So now what we are supposed to do is that, okay. So now for question 4, what is being asked is that if density of water is 1000 kg per meter cube, H1 is 6.02 centimeter, what will be the density of the fluid marked as mercury? So what is asked, if density of water is 1000 kg per meter cube and H1 is given as 6.02 centimeter. So here H1 is given as 6.02 centimeter. So density of water density is given as 1000 kg per meter cube, and we are asked to find what will be the density of the fluid marked as mercury. So here we are asked to find what will be the density of the fluid which is marked as mercury. So we know how to do balance with respect to height. So we do the pressure balancing. So it is nothing but rho GH approach. So first let us write what is given over in the question. So first one, it is given that density of water is 1000 kg per meter cube and H1 is 6.02 centimeter and density of oil is 780 kg per meter cube. We are given specific gravity, which is nothing but into 1000 gives us a density of oil. So it is 780 kg per meter cube, and water density is 1000 kg per meter cube, and H1 is 6.02 centimeter. So we are asked to find density of mercury. So first, as I mentioned, we will do the pressure balancing. So between these two columns, so let us consider this as 1 and this as 2 and this as 3. So we will do between 2 and we will, whichever we do, we will get the final solution. So first we will do between these two. So it is rho water into G into 27, that is 27 centimeter. Ideally it should be like, I should have changed units accordingly, but here since it is, since I have used units consistently, I haven't done that. But yeah, rho water, rho GH, rho density of water into G into H. H here is 27 centimeter plus rho mercury, density of mercury into G into H1 equal to rho of mercury into G into 8. So we are balancing between these two. So we are doing in such a way. Now what are all the unknown things? Here H1 is given as 6.02 centimeter and density of water is given as 1000 kg per meter cube. So now we are substituting everything back in the equation. So that will give us G is getting cancelled because it is present throughout the equation. So 1000 into 27 plus density of mercury is unknown into 6.02 equal to density of mercury into 8. So now we know what are all the things present in the equation and what are all the unknowns. So we have substituted everything known in the equation and we are left with density of mercury. So we are just taking this to the other side. So we will be getting 1.988 minus 6.02 will give us density of mercury into 1.98 equal to 27 into 1000. So that will give us 27,000. So rho mercury divided by 27,000 divided by 1.98. So that will give us density of mercury as some 13,600 kg per meter cube. So that is how we get the density of mercury. So I hope it is clear. So what we are doing, we are just doing the pressure balance between the two columns. So first one, it is having water and mercury, and the second one we are having pure mercury. So we know the density of water, we don't know the density of mercury. So we are doing density of water into this height plus density of mercury into this height equal to density of mercury into this 8 centimeter. So we are taking the unknowns to one side and knowns to the other side. So we will be getting this, and we are just dividing this by 1.98 and we will be getting the density of mercury. Since every unit of height is in centimeter, it didn't affect, but otherwise it is always wise practice to change unit in a single SI unit or any unit, but it should be consistent. Here it is not consistent. Why? Because rho is in kg per meter cube, whereas this one is in centimeter. But since it is, I mean, it is throughout, it didn't affect, but it is not a very good practice. But yeah, we arrived at the final answer, that is 13,600 kg per meter cube, which is the density of mercury. So in the question we were asked to find the density of the fluid marked as mercury, and we got the answer as 13,600 kg per meter cube. So now we will go to question 5. So question 5 is again from the similar figure. So we need to arrive at certain things. So what is the value of H2? So here we are asked to find the value of H2, that 2 in centimeter. If H1 is 7 centimeter and water height in the first system is 40.8 centimeter instead of 27 centimeter. So here we were given that water height is, just a minute. Water height is not 27 centimeter, rather it is given as 40.8 centimeter, and H2 we are asked to find. So H1 is also given as 7 centimeter. In the previous question it was some 6.02, but now it is changed. So now we need to find what is the height H2. So similar thing how we did last problem, we need to do it. Now yeah, we'll start with that given. So first, given density of water is given as 1000 kg per meter cube, and H1 now it is changed to 7 centimeter, and density of oil it is 780 kg per meter cube, and restore all the things that are the same. So now again we will do the balancing. So first we need to find what is the value of H2, and solution we are again doing the pressure balance. Now what between what and what we are doing? We are doing it between this and this. Okay. Actually, like I just changed the numbers. So because of that, if you do math between these and this, it might give you a wrong answer. So yeah. So I mean, just because I changed the values to ensure you have a lot of practice problems. So what we can do is, we can just, yes, this is better. So now we are just balancing between the first column and the last column, because you can do between second and third also, but since here numbers are different, it might lead to a different result. So that's why I cut out this middle column for this particular problem. Um, so yeah. So now what we are doing, it is 40.8 centimeter instead of 27 centimeter. So I'm just substituting 40.8 into density of water into G plus density of mercury into G into H1. H1 is 7 centimeter and rho mercury into G. Okay. Again it is second. And okay, actually I changed few numbers here. That is the issue. This 40.8 centimeter. Similarly, one more thing which I changed is, it is I did as 8 centimeter. H1 is 7 centimeter. Yeah. I think that is fine. So yeah, we are just balancing between these two, rho water into G into 40.8 plus rho mercury. Now this one is missing. I mean, we are not sure which is mercury right here, that's why. I mean, it is because I just changed few numbers to give a different problem. So this is kind of became confusing because of that. But anyway, I mean, the main thing is we need to understand how the problem is being done. Rest or all things, if you are clear with the concept, you can do any problems. So yeah, again, we are just doing pressure balance. Rho water into G into 40.8 plus rho mercury into G into H1 equal to rho mercury into G into 8 plus rho oil into G into H2. So 1000 into 40.8 plus mercury density we found from the last problem, and that was given as 13,600, and 13,600. So into 7 equal to 13,600 into 8, that is this one, plus 780 into H2. So which we will be getting it as 40.8 into 1000, it is 40,800 plus we are 95,200, which we get from this, equal to 13,600 into 8 plus 780 into H2. So now what unknown we are left with in this equation? We are left with H2. H2, so we are taking everything else to the other side. So after that we will be getting this will give us 13,000 something, and minus, I mean not 30, 1,30,000 something, and minus 1 lakh, which will give us 30,000 something approximately, divided by 780 will give us H2, that is in 34.87 centimeter. So here what we need to be clear is that since everything is in centimeter, H2 is also in centimeter. Unit is very important when we are talking about any problems. So be conscious with the units. One more thing I need to say is, I'll just cross check the calculation once. 4800 plus 95,200. 4800 plus 95,200 minus 108800 minus 108800 divided by 780. Yeah, it is 34.87 centimeter, that is right. One more thing I just request you, because since I changed every number, there might be some issues with respect to numbers. So please bear with me, just understand the concept. Next time I'll check one more time properly. Yeah, that is fine, I guess. Yeah, and there was one more problem also, right? The first problem, Pascal. This also is 0.3 Pascal. There are any numerical errors, just bear with me. Yeah. Now, I hope concept wise this problem is clear. In fifth question alone, there is some mismatch because it kind of like new numbers didn't match properly. But yeah, the problem is similar to how we did in question 4. If you are clear with question 4, it is question 5 is the same. Water in the we'll remove this also. So similar concept, but just numbers were changed, so it kind of led to some confusion. But anyways, so also note in the question itself, it was asked what is the height in centimeter. So you need to give the answer in centimeter. So that is the thing. Now, yeah, we'll now move on to question 6. So question 6, again we have a flow system wherein water from three pipes are joined at one point, and it is flowing as one flowing together in the single pipe thereafter. So we are given the diameter of the three pipes, three inlet pipes, D1, D2, D3, and together it is getting mixed here and exiting via pipe D4, pipe of diameter D4. So what is given in the question statement is that three pipes steadily deliver water at 20 degrees Celsius to a large exit pipe. So here we are able to see that diameter of D1, D2, D3 are smaller than D4. So three pipes steadily deliver water at 20 degrees Celsius to a large exit pipe as shown in figure 3. So this is figure 3. The velocity V1 is equal to 6 meter per second. So velocity for V1, that is the flow in the pipe. Let us consider three pipes, so that will be easier for us to understand. So this is pipe 1, this is pipe 2, so this is pipe 3. So this is exit pipe, that is pipe 4. So we are having three pipes delivering water to a pipe larger pipe 4. So velocity in pipe V1 is given as 6 meter per second, and the exit flow rate is given. So we are given velocity in pipe V1, pipe 1, and the exit flow rate we are given. So it is known that in this case flow rate in pipe 1 is equal to that of flow rate in pipe 2. So what is mentioned here is that flow rate in pipe 1, that is, where is my cursor? Okay, here. So it is Q1 equal to Q2. That is given in the question statement. Flow rate in pipe 1 is equal to flow rate in pipe 2. So I hope we are clear with the question statements. So what is given? Let us read the question one more time. So we are given three pipes which are steadily delivering water at 20 degrees Celsius to a larger pipe, and we are given the diameter of three pipes D1, D2, D3, and the large exit pipe is diameter is D4, and we know the velocity of the flow water flow in pipe 1, and also similarly we know the flow rate of the water at the larger exit pipe, that is Q4 we know. Now we need to find few things from this particular problem, and so I hope we are clear with the problem statement that is picturized over here. So yeah, we'll move to the questions. Okay, we are asked to find. So here we need to find. So first we need to find V2. So velocity of the water at pipe 2. So here we need to find the velocity of the water at pipe 2. So it is a very easier case actually. So first what we need to do is we need to do the balance, mass balance. So on doing that we will be getting. So what is continuity equation state? It states that rho A V is equal to constant. So that is what we are going to apply over here as well. So since it is an incompressible system and we know that the fluid is water at 20 degrees Celsius, we can keep the density as a constant and we can cancel it throughout the equation. So now to find V2, what we are doing is that we are given velocity V1 as 6 meter per second. Sorry, exit flow rate we are given as, do we have a picture here? If not, I'll add that. Oops. Yeah, it will be easy for us to picturize, that's it. I'll keep it for every image. So, I mean, it is just a continuous question with a series of questions actually. So, V2 we are asked to find. So, what else is given? We are given velocity at in the pipe 1 is 6 meter per second, and exit flow rate is given as Q4 is 120 meter cube per hour. And flow rate in pipe 1 is equal to flow rate in pipe 2. It is given in the question. So Q1 is equal to Q2. Now we will do the balance as I mentioned. So it is to find V2. So what we are doing is flow rate. So like flow in is equal to flow out when there is no accumulation. So Q1 plus Q2 plus Q3 is equal to Q4. So Q1 is equal to Q2. So we are just substituting Q2 is equal to Q1 and we will be getting 2 times of Q1 plus Q3 equal to Q4. So now we are just continuing from that. 2 times of Q1 plus Q3 is equal to Q4. So Q4, that is exit flow rate, is 120 meter cube per hour. So what is, again we are just converting it into meter cube per second, because in velocity we are giving it in meter per second, so it is best to convert everything in flow rate to meter cube per second. So how do we convert meter cube per hour to meter cube per second? We divide it by hour to seconds, we divide it by 3600. So 120 by 3600 gives us 0.0333. If there is any numerical error, if you find it now, let me know, or if you are finding it in future, Please don't bother. I'll try to be make it perfect next time, but still this time bear with me. So 2Q1 plus Q3 is equal to 120 by 3600, which is giving us 0.0333. So now V1 is given as 6 meter per second, and we know A1. So Q1, how do we get the flow rate? We get flow rate as Q is equal to A into V. That is what we do, right? Rho AV is equal to constant. In continuity equation, AV is equal to flow rate. So A is nothing but area, cross-sectional area, and we have values of D1, D2 and D3 and D4 as well. So now, since we know V1, since we know D1, we can get Q1, right? So we can get Q is equal to area into velocity. So A1, if we calculate, we know V1, so we can get Q1. So A1 is equal to pi by 4 D1 square. So it is D1 is equal to 4 centimeter. So 4 into pi by 4. It is 12.56 centimeter square. So area of this particular pipe is, cross-sectional area of this particular pipe is 12.56 centimeter square. So now we know velocity, flow velocity, and also we know the cross-sectional area. So with both of that information, we will be getting the flow rate. So 12.56 into 10 power minus 4, because we are using the unit of area in centimeter square, we need to convert it into meter square when we are doing it for flow rate, because velocity is in meters. So 12.56 into 10 power minus 4 into 6 gives us 7.536 into 10 power minus 3, or here in this question it is given as 75.36 into 10 power minus 4 meter cube per second. So clear? Now we got Q1. Alright, so Q1 is equal to Q2. So Q1 is equal to Q2. So Q2 is also 75.36 into 10 power minus 4 meter cube per second. So now if we know Q2, we can get the area because diameter is given. So we know Q2, we know A2. What we can find? We can find V2. Velocity is asked in the question, so we can find the velocity in this way. So now we are doing that only. So area 2 is equal to pi by 4 D2 square. Again D2 is 5 into 5 divided by, into 3.14 divided by 4. So it gives us 19.625 centimeters square. So we know A2, we know Q2, we can get V2. How do we get V2? V2 is equal to Q2 by A2. So V2 is equal to Q2 by A2. So Q2 is equal to 75.36 into 10 power minus 4 meter cube per second divided by 19.63 into 10 power minus 4. Because we are converting centimeter square into meter square. Alright, 75.36 divided by 19.63. So that gives us 3.84 meter per second. So that is how we get V2, that is velocity in pipe 2. So let us go through the problem once again. So it will be very clear to you, because it would be so much information at once. But if we look at it once again, it will be clear. So I'll just keep this slide only, or okay, we can go to the previous slide only. Okay. We are asked to find velocity in pipe 2. What are all the information given to us? We are given the velocity of the fluid in pipe 1. So this velocity we are given, and this flow rate we are given, that is exit flow rate, we are given as 120 meter cube per hour. Now what else is given from the figure? We are given the diameter of each pipes. So we are having 3 pipes attached to 3 pipes coming, and it is attaching to one large pipe. So obviously what will happen, all the flow rate from the inlet pipe added together should be equal to the outlet flow rate, right? When there is a steady state and when there is no accumulation, this is what will happen. When everything summed up should be equal to the exit flow rate. that is the case when there is no accumulation and when there is a steady state being done, steady state being followed. This we can see in any pipe flow also, right? If we are having 2 or 3 pipes which are having water flow, so once water from all 3 pipes are coming and attaching at a single point and they are flowing from there, the flow rate or the volumetric flow rate in each pipes added together will give us the exit flow rate when there is no blockage, when there is nothing stopping the flow of water in between. So that concept only we are doing it here. That is continuity equation is conserved. Mass is conserved. That is mass conservation we are doing. So Q1 plus Q2 plus Q3 is equal to Q4. That is the basic thing. So apart from that, we know the area of each pipe. So what is Q? Q here is volumetric flow rate. So how do we get volumetric flow rate? We get it by multiplying cross-sectional area into velocity. So area into velocity you can do unit wise also. Area is meter square, velocity is meter per second. So that multiplying meter square by meter per second will give us meter cube per second, which is volumetric flow rate. So that is the only concept which we are applying. So Q1 plus Q2 plus Q3 is equal to Q4. Since area in each pipe is varying, velocity will also be varying, and based on that the numbers will vary. Again, please don't calculate physics or something from the numbers given over here, because numbers are given by me. So it might not be very accurate representation of physics. So just learn the concept and applying it to real world problems will give you a proper solution. So Q1 plus Q2 plus Q3 is equal to Q4. Now what is given in the question? It is given in the question that flow rate in pipe 1 is equal to flow rate in pipe 2. So Q1 is equal to Q2. So that concept we are applying here. Q1 plus Q2 plus Q3 is equal to Q4. So Q2 is equal to Q1. Q1 plus Q1 plus Q3 is equal to Q4, which is 2Q1 plus Q3 is equal to Q4. So now 2Q1 plus Q3 is equal to Q4. Q4 is 120 meter cube per hour, which we are converting into meter cube per second by dividing by 3600, because 1 hour contains 3600 seconds. So after which we will be getting meter cube per second. Yeah. Now we know V1, V2, V3, V4 are unknown. So V1 is 6 meter per second and D1 is given. So V1 into A1 will give us Q1. So A1 we can calculate. How do we calculate A1? Since it is a circular pipe, we can take it as pi by 4 D1 square. So I mean circular is the cross sectional area. It is a cylindrical pipe, so cross sectional area will be circular. So cross sectional area is pi by 4 D square, or it is pi r square, whichever. So pi by 4 d square is giving us area of pipes. I mean cross sectional area of pipes. So A1 we are getting it as 12.56. So now A1 we know, B1 we know, Q1 we can calculate. So Q1 we can get it from here. So since in the question it is mentioned Q1 is equal to Q2, we take Q2 as 75.36 into 10 power minus 4 meter cube per second as well. And after that, what information is available for pipe 2? Pipe 2 has area information we can calculate, and flow rate, volumetric flow rate we have. Now based on that we can easily calculate velocity, flow velocity in pipe 2. So A2 is equal to pi by 4 D2 square is equal to 3.14 into 5 into 5 by 4, which will give us this area, and based on that we can get V2 as well. So V2 is equal to Q2 by A2. Q2 we know, A2 we know, substituting it gives us V2 is equal to 3.84 meter per second. Now that is how we got V2 value. So I hope it is clear. If you want, just take some take a minute to understand if you have any doubts, because next two problems are actually based on or continuation of this particular problem only. So I'll give you people 1 minute, just understand the question clearly. Later we can move on to next question. All right, I am. If you have any doubts, you can stop me anytime. Now we will go to next question actually. So as I mentioned, it is a continuous problem. So maybe like after this two problems, we can take a small break actually. Yeah. So now what we got Q1, we got Q2, we got V2 as well. Now what else we can get from here? We can get Q3 and V3, and we can get V4 as well. So those are the two questions coming up. So what is being asked in question 7? It is asked that we have to find V3, that is flow velocity in pipe 3. So now we know Q1, we know Q2, we know Q4. So we can easily obtain Q3. So just substitution. So we are just continuing the solution from previous question. So question 6. So Q1 plus Q2 plus Q3 is equal to Q4. So Q1 is equal to Q2. So 2Q1 plus Q3 is equal to 0.033. So Q1 also we calculated as 75.36 into 10 power minus 4 meter cube per second, and which we are substituting over here. So 2 times of Q1 plus Q3 is equal to 0.0333. So 2 into 75.36 into 10 power minus 4 will give us 0.015072. So Q 0.015072 plus Q3 is equal to 0.033. So now we are taking that 0.015072 to the other side. So that will be 0.0333 minus 0.015072, or we can consider 0.015. So we will be getting Q3 as 0.0182 meter cube per second. So now we obtain the value of Q3 as well. How did we get? It is Q1 plus Q2 plus Q3 plus Q1 plus Q2 plus Q3 is equal to Q4. So apart from Q3, everything else is known. Q1 we know, Q2 we know, Q4 also we know. So Q3, by back substitution, we will be getting the value of Q3. So which we got it as Q3 is equal to 0.0182 meter cube per second, and based on that we can get V3. Sorry, Q3 we got. Now we can calculate V3. V3 is equal to Q3 by A3. Q3 is equal to 0.0182 meter cube per second. A3 is equal to cross-sectional area of pipe 3. So it is again a circular cross-sectional area. So it is pi by 4 d3 square. So d3 here is 6. So 6 into 6 into 3.14 divided by 4, which will give us 28.26 centimeter square, or 28.26 into 10 power minus 4 meter square, which we are using in V3. V3 is equal to Q3 by A3. So Q3 we know as 0.0182 divided by A3. A3 is 28.26 meters centimeter square. So here 28.26 into 10 power minus 4. So which we will be getting as 10 power minus 4 0.0182 divided by 28.26 into 10 power minus 4. So we will be getting it as 6.4 meter per second. Yeah, 6.44 meter per second. Ideally, the velocity should have been anyways. Now what we are going to do is that this is how we get V3, that is flow velocity in pipe 3. We got it as 6.44 meter per second. Now we'll go to question 8. So question 8 is again derived from this particular question, and we'll be asked to solve for something which we'll see now. So V4 is equal to dash. So we are asked to find V4. So finding V4 is one of the easiest tasks. Why? Because we already know Q4. We just need to calculate for A4. If we calculate for A4, we can easily calculate V4. So again we are continuing the solution from 6th problem. So Q4 is 120 meter cube per hour, which we are converting into meter cube per second by dividing the 120 by 3600. So we will be getting it as 0.033 meter cube per second. Now we need to know area of the exit pipe. So exit pipe diameter is given as 9 centimeter. So we are calculating the area as pi by 4 d square. Again it is 3.14 into 9 into 9 divided by 4, 63.585 centimeter square. Now if we divide Q4 by A4, we will get V4. So 0.033 divided by 63.585 into 10 power minus 4. So basically it is 5.19. Okay, 5.033 divided by 63.5. 0.033 divided by 63.59. Okay, basically it depends on the number of digits which you are taking, but it won't matter actually. If you take 4 digits, answer should be around 5.2, so it is fine. Whichever number you get after that, it will be fine. So 5. 5.24 or 5.19 depending on the number of significant digits which we take after the decimal point. So V4 is 5.24 meter per second. That is the velocity of the water in the exit pipe, that is D4 or pipe 4. So that is how we get answer, the solution for this. So these are the similar problems. Now we will go to question 9 actually. Okay. The coming problems are a kind of similar problems. So we'll just take a 2-3 minutes break. We'll come back again. It is 4:18, I guess. Yeah, 4:19. We'll come back in 4:22. Start. Okay, yeah, we'll start again. Is there Okay, yeah, we'll start and we will continue. Okay. So coming up problems are having some similarity. So we just need to change it according to the questions. So kind of interesting problems only. So first one is question 9. Given the steady incompressible velocity distribution, u is equal to ax, v is equal to by, and w is equal to cx square y square, where a, b, c are constants, this flow satisfies the continuity equation. Option A, if A equals B. Option B, if A equals B plus C. Option C, if A equals B minus C. Option D, if A equals minus B. Option E, if A equals minus of B plus C. Option F, if for any values of A. Okay. So, okay. So, for what is asked in the question, we need to find for what value of A this equation satisfies the continuity equation. So, that is what we need to know. So, what is given? We are given three velocity components u, v and w. U is equal to ax, v is equal to by, and w is equal to cx square y square. So, what is incompressible continuity equation. So it is dou u by dou x plus dou v by dou y plus dou w by dou x, dou w by dou z equal to 0. So when we put, so here it is given that when will the continuity equation be satisfied. So that is a question. So if we substitute everything in that equation, we can get to know when the equation will satisfy the continuity equation. So basically we need to derive, take the derivative and substitute in the equation. That is the thing we need to do here. So first let us see the answer anyway, because answer is actually option D, if A equals minus B. So but how do we arrive at the equation? So what is given? Given u is equal to ax, v is equal to by, and w is equal to cx square y square. So find which value of a satisfies the continuity equation. So now how do we get the value of a for which the continuity equation is satisfied? So first we need to write the continuity equation. Dou u by dou x plus dou v by dou y plus dou w by dou z equal to 0. So now dou u by dou x is a plus dou v by dou y is b, dou w by dou z is equal to 0. We will substitute the derivatives in the equation. So dou u by dou x is a, dou v by dou y is b, and dou w by dou z is 0. So we are substituting everything back in the equation, so that will give us a plus b plus 0 should be equal to 0. So what will the a value be? A value will be equal to minus b. B we are taking it to the other side, so it will become a equal to minus b. So when a is equal to minus b, the equation of continuity is satisfied. Are we clear? So what was the question? In the question it was asked for which value of a the continuity equation will be satisfied. So for that we are given u component velocity, x, y and z component of velocity, and u is a function of a, u is a function of x, v is a function of y, and w is a function of x and y. So we are just substituting everything in the continuity equation and solving for a. So the equation is satisfied when a is equal to minus b. So a is equal to minus b. If you put minus b here, this becomes 0. So continuity equation is satisfied. So that is how we do things. So a is equal to minus b, continuity equation is satisfied. So I hope we are clear over here. Now we will go to next question. In question 10 it is asked that the convective acceleration in the x direction is dash. The convective acceleration in the x direction is dash. So basically the question is continuing from the previous question for the values of u, v and w. So now we need to find the convective acceleration for that. So option A, it is 2ax square y. Option B, a square x. Option C, 2b square xy. Option D, 2bxy square. Option E, 2cx square y. Option F, 2abx square y. So finally the answer is option D, a square x. So we'll see how to do that before checking for the answer anyway. So first, what was asked in the question? We are asked to find the convective acceleration in the x direction. So ax. So first we'll write what is given. So we are given u, v and w functions, velocity components. So this is from the previous question actually. Continuation of previous question. So u is equal to ax, v is equal to by, c is equal to, u is equal to ax, v is equal to by, and w is equal to c into x square y square. So now what are we asked to find? We are asked to find the convective acceleration in the x direction.
So now what is the formula for getting the convective acceleration in the x direction? It is Ax is equal to u into dou u by dou x plus v into dou u by dou y plus w into dou u by dou z. So since it is in the x direction, we are taking all the derivatives with respect to the u velocity component. U into dou u by dou x plus v into dou u by dou y plus w into dou u by dou z. So now since every derivative is we are taking with respect to u velocity component only, so now we can consider the saloon. Dou u by dou x is a. It is not a function of y. U is not a function of y. So dou u by dou y is 0. Again u is not a function of z. So dou u by dou z equal to 0. So here we are substituting everything back in this particular formula. So Ax is equal to u into dou u by dou x plus v into dou u by dou y plus w into dou u by dou z. So dou u by dou x only remains. So Ax is equal to u into dou u by dou x. So it is a into u. So again what is u? U is Ax. So it becomes a into Ax. So it becomes a square x. So a x into, that is u is Ax. So Ax into a, it becomes a square x. So I hope we are clear in this question. So I'll repeat once again. So in this question we are asked to find for the convective acceleration in the x direction. So convective acceleration is given by this u into dou u by dou x plus v into dou u by dou y plus w into dou u by dou z. Now we have to find every derivative of u with respect to x, y and z. So now we have u as Ax. So dou u by dou x is a, but u is not a function of y and z. So dou u by dou z and dou u by dou y and dou u by dou z becomes 0. So it becomes Ax is equal to u into dou u by dou x. So dou u by dou x is a, u is Ax. So Ax into a, it gives us a square x. So that is how we arrive at the answer. So answer is option B, a square x. So I hope you are clear now. So now we can go to next question. We have 4 problems left. So out of that, I think 3 problems are from similar problem statement. So in the question, it is given that a frictionless incompressible steady flow field is given by u is equal to Ax, v is equal to by and w is equal to c into x square y square, where a, b, c are constants in arbitrary units. Let the density be rho naught, which is a constant, and neglect gravity. So this is the problem statement given for the coming up problems. So what is given? We are given a flow field given by u is equal to Ax, v is equal to by and c is equal to, v is equal to by, w is equal to c into x square y square. So this are the same fields given in the previous question also, and here a, b, c are constants and density is given as rho naught, which is a constant. So it is an incompressible flow field and it is a steady flow field and it is a frictionless flow field, and we are asked to neglect density. So that is the question. So now we have to solve the problems in the coming up slides. So we'll see first what is asked. In question 11, what is asked is that find the expression for pressure gradient in the x direction. So all the coming up problems are similar. So we will be asked to find the pressure gradient in the x, y and z direction. So that is find the expression for the pressure gradient in the x direction. So first option A, it is 2 times of rho naught into A into B into x square y. Option B, 2 times of rho naught A B x y square. Option C, 2 times of rho naught c square xy. Option D, 2 times of rho naught into a b square xy. Option E, 2 times of rho naught a b c xy square. Option F, rho naught a square x. Option G, 1. Option H, 0. So we need to identify the expression for the pressure gradient in the x direction. So answer, we can say it as F rho naught a square x. So we will see the answer first. So for all the coming up problems, please make sure you understand the concepts. Don't be like focusing on the numerics, that is numbers or expressions. Just understand how to solve the problems, because that will give us an idea how to solve similar problems, because similar problems are only asked in the assignments. Maybe they can come in your final exam also. So that is the thing. So in question 11, how we are going to solve, we are asked to find the pressure gradient in the x direction. So first what we need to do is we will just list out what are all the things given. So first one, we are given frictionless, and it is stated incompressible, it is stated steady flow. So u is a function of ax, v is a function of by, and w is cx square y square. So A, B, C are constants, and density is rho naught, which is constant, and we are asked to neglect gravity. So find the pressure gradient in the x direction. And now we have to first solve for the continuity equation and solve for the x direction momentum conservation equation. So two equations we need to solve and see how it is behaving. So first one, continuity equation for incompressible flow is given by del dot u is equal to 0. So basically it is dou u by dou x plus dou v by dou y plus dou w by dou z equal to 0. So this is the thing we solved in the previous problem, question 10 as well. So dou u by dou x is a plus dou v by dou y is b plus dou w by dou z is 0. A plus b is equal to 0, so a is equal to minus b. Alright, so similar to how we got in the previous question, a is equal to minus b, that is the thing. So now since we got a, we need to solve for the momentum conservation in the x direction. So we are going to that part. Navier-Stokes equation, in general we can write it as dou u by dou t plus del dot u equal to mu, that is mu by rho into del dot del u plus g minus 1 by rho delta p. So this is the overall Navier-Stokes equation comprising of all the three directions, generalized equation. So specifically when we are talking about x direction momentum conservation equation, we can write it in this format: rho into du by dt equal to minus dou p by dou x plus mu into dou square u by dou x square plus dou square u by dou y square plus dou square u by dou z square. So what was given in the question? Frictionless, so mu becomes 0, incompressible, steady state, and we are asked to neglect the gravity. So first we will expand this term, that is rho into du by dt. So we will be we will be getting it as, all the terms become 0. We are asked to neglect gravity and we are frictionless, so these two terms become 0. So rho du by dt is equal to minus dp by dy. So if we expand this term, we will be getting rho dou u by dou t, so which becomes 0 because it is a steady state, plus u into dou u by dou x plus v into dou u by dou y plus w into dou u by dou z. So this is the LHS term and this is the RHS term. So we are asked to find the pressure gradient in the x direction. So u is ax. So u is not a function of y and u is not a function of z. So these two terms become 0. And we will be left with this particular term alone. So dou u by dou x is a. So u into dou u by dou x is a square x. Dou u by dou x is equal to a, and u is not a function of y, u is not a function of z. So these two terms become 0. And substituting back, we will be getting rho naught into ax into a equal to pressure gradient. So rho naught ax square, rho naught a square x is the pressure gradient. So pressure gradient is given by rho naught A square x. So that is how we get the pressure gradient in the x direction. So that was our answer as well, rho naught A square x. So rho naught A square x, option F. So basically what was given, we are given a certain statements, frictionless incompressible steady flow field, and we are given u, v and w velocity components, and we are asked to neglect gravity and we are asked to find the pressure gradient in the x direction. So we solved the continuity equation and got values of a as a function of b, that is a is equal to minus b. So this we obtained from the solving the continuity equation. Next we substituted back in the x direction momentum conservation equation. So the equation is this, rho into du by dt equal to minus dou p by dou x plus mu into dou square u by dou x square plus dou square u by dou y square plus dou square u by dou z square plus rho gx. So we neglect gravity, so this becomes 0. Frictionless, so this becomes 0. So we will be left with only these two. And this we can expand as dou u by dou t plus u into dou u by dou x plus v into dou u by dou y plus w into dou u by dou z. Since it is a steady flow, the first term actually became 0. So I haven't written over here. But it comes. So, but it is a steady flow. We haven't included that here. So coming back, so we have to substitute. We have to solve for these and substitute back, and we will get the pressure gradient. So u is a function of x alone. So these two terms become 0. So u is equal to ax. Dou u by dou x is equal to a. So u into dou u by dou x becomes a square x. Rho is rho naught. So rho naught a square x is the final answer. So this is the problem. So the next two problems are similar problems, but we are asked to find in the y direction and z direction respectively. So that is the next two problems. If we are clear with this problem, we can easily solve the next two problems. So I hope it is clear. If you have any doubts, you can ask. So yeah, at last also we can ask, we can discuss our doubts. So yeah, now we will go to question 12. In question 12, what is asked? Find the expression for the pressure gradient in the y direction. So as I mentioned, it is a similar problem. So instead of x direction in the previous question, now we are asked to find the pressure gradient in the y direction. So that is the only difference. So yeah, so now we'll see how to do that. So first let us look at the options anyway. Option A, it is rho naught b square y. Option B, 2 times of rho naught ab x square y. Option C, 2 times of rho naught c square xy. Option D, 2 times of rho naught a b square xy. Option E, 2 times of rho naught a b c xy square. Option F, 2 times of rho naught a square x square. Option G, 1. Option H, 0. So answer is actually option A, rho naught b square y. So it is actually similar to the last problem where we got rho naught a square x. So similar thing only, because here v is a function of by. V is a function of y and it is not a function of x and z. So that's the thing. So anyway, we will see how to solve that. First, again, it is just a repetitive because similar problem. So what was given? It was given that frictionless incompressible steady flow field and u, v and w components are given as ax, by and cx square y square respectively. A, B, C are constants and we are asked to neglect gravity. We are given density as rho naught, which is a constant. We are asked to find the pressure gradient in the y direction. Similarly, we have the continuity equation and we are solving for the continuity equation for incompressible flow. Dou u by dou x plus dou v by dou y plus dou w by dou z equal to 0. So dou u by dou x is a, dou v by dou y is b, dou w by dou z is 0. So we are getting a plus b plus 0, which should be 0. So on that condition, a becomes minus b. So now a equal to minus b. So now we have to solve for the momentum conservation equation in the y direction. Previously we did for the x direction, now we are doing it for the y direction. So this is a generalized Navier-Stokes equation, and specifically for the y direction we will be getting it as rho into dv by dt equal to, it should be v. Rho into dv by dt equal to minus dp by dy plus mu into dou square v by dou x square plus dou square v by dou y square plus dou square v by dou z square plus rho gy. So again it is a frictionless, and neglecting gravity these two terms become 0, so we will be left with only these two terms. So which we can rewrite as rho into u into dou v by dou x plus v into dou v by dou y plus w into dou v by dou z equal to pressure gradient. V is a function of y. V is equal to by. So it is a function of y. So it becomes dou v by dou x is 0. Dou v by dou y is b. And dou v by dou z is 0. Which is equal to, we have to substitute back. So rho is rho naught. And these two terms become 0. V is by into b. So b into dou v by dou y. So by into b equal to pressure gradient. So it is rho naught b square y is the pressure gradient in the y direction. So I hope it is clear. Pressure gradient in the y direction is given by rho naught into b square y. So that is the thing. Now we will move on to question 13, which is again pressure gradient in the z direction actually. So find the expression for the pressure gradient in the z direction or z direction, whatever. So now similar procedure which we are going to follow, which we followed in the last question. But in the momentum conservation equation, we will be writing it in the z direction. So options given are option A, rho naught a square x, option B, rho naught b square y, option C, rho naught c square xy, option D, rho naught ab square xy, option E, rho naught ab cxy square, option F, rho naught a square x square, option G 1, option H 0. So answer is actually option H actually, which is 0, because based on the previous solving procedure itself we can see that w is a function of xy and it was not a function of z, and so there was not a major impact which it produced. So I'll just show the solution once. Just give me a moment. I'll just see the solution till then. Actually, it should. Okay, I'll just check the answer while doing. I'm thinking small difference. Anyways, so given it's a frictionless, incompressible, steady flow field, u is a function of ax, v is a function of by, and w is a function of cx square y square, and density is constant. Neglecting gravity, we are asked to find the pressure gradient in the z direction. And similar to previous question, we solve for the continuity equation for the compressible flow, and we doing dou u by dou x plus dou v by dou y plus dou w by dou z equal to 0, and u is equal to ax, v is equal to by, and w is equal to cx square y square, and density is rho naught. So based on that, we will be having getting the answer as a is equal to minus b. So after substitution, we will be, here I wanted to change. So we solved for the continuity equation and saw that a is equal to minus b satisfy the continuity equation. So Navier-Stokes equation in generalized form is this, and in the z direction momentum conservation equation, it is given by rho into dw by dt is equal to minus dou p by dou z plus mu into dou square w by dou x square plus dou square w by dou y square plus dou square w by dou z square plus rho gz. So it is a frictionless, incompressible, steady flow neglecting gravity. And as we know, these two terms get cancelled because of frictionless and neglecting gravity thing given in the question. So we will be left with rho into dw by dt equal to minus dou p by dou z. So now dou p by dou z. So pressure gradient is equal to this. So now W is equal to C into x square y square. So here W is a function of x and W is a function of y, but W is not a function of z. So we need to do it accordingly. So dou W by dou x. So dou W by dou x will give us, once again, dou W by dou x will give us C into I'll just solve it again once again. C into 2x into y square, and dou W by dou y will be again C into 2y into x square. Dou W by dou z will be 0. This will be u into, dou W by dou x. Once again. Okay, if there is any change, I'll while uploading the PPT, I'll upload it rightly. But yeah, dou W by dou x is equal to C into 2x into y square. Dou W by dou y equal to Cx square 2y. Dou W by dou z equal to 0. So we are just substituting everything back. Substituting back, we will be having minus dou p by dou y equal to rho naught into, oh, it should be dou z. dou P by dou Z equal to rho naught into U into C dou W by dou X, C into 2xy square plus V into Cx square 2y, that is dou W by dou Y. So this becomes U is Ax, V is By, that also we are substituting back. So A into C x square y square, 2 times of A C x square plus 2 times of B C x square y square into rho naught. So A is equal to minus B. So substituting that, it will give us 0 actually. So pressure gradient is 0. So that is the thing. A is equal to minus B will give us pressure gradient as 0. So yeah, that is for question 13. Now we have question 14, which is as follows. Consider the incompressible flow field with velocity components u is equal to 0, v is equal to minus 2y and w is equal to 2z, and pressure is given as P is equal to minus 2 rho y square minus 2 rho z square. Neglect gravity and assume constant viscosity. Does this velocity field satisfy Navier-Stokes equation? So we are given velocity fields u is equal to 0, v is equal to minus 2y and w is equal to 2z, and we are given pressure field, and we are asked whether this velocity field satisfy Navier-Stokes equation. So first, option A yes, option B no, option C unable to determine, option D may or may not depending on the initial and boundary conditions, option E depends on Reynolds number, option F depends on whether it is a liquid or a gas. So answer is actually option A, yes. We will see how. So first one, it is given that u is equal to 0, v is equal to minus 2y and w is equal to 2z. So continuity equation for incompressible flow is given as del dot u is equal to 0. So dou u by dou x plus dou v by dou y plus dou w by dou z should be equal to 0. So dou u by dou x is 0, dou v by dou y is minus 2, dou w by dou z is 2. So which we are getting from these values. So substituting back, we will getting as we will be satisfying the continuity equation. So continuity equation is satisfied. So now coming to Navier-Stokes equation. So generalized equation is dou u by dou t plus del dot u equal to nu into del dot del u plus g minus 1 by rho del p. So in the x direction, it is rho into u into dou u by dou x plus v into dou u by dou y plus w into dou u by dou z equal to minus dou p by dou x plus mu dou square u by dou x square plus dou square u by dou y square plus dou square u by dou z square plus rho gx. So here what things is steady state. So the first dou u by dou t term became 0. We have it included here. So similarly, y direction we have equation like this: rho into u into dou v by dou x plus v into dou v by dou y plus w into dou v by dou z equal to minus dou p by dou y plus mu into dou square v by dou x square plus dou square v by dou y square plus dou square v by dou z square plus rho gy. And z direction, it becomes rho into u into dou w by dou x plus v into dou w by dou y plus w into dou w by dou z equal to minus dou p by dou z plus mu into dou square w by dou x square plus dou square w by dou y square plus dou square w by dou z square plus rho gz. So yeah, so what we are asked to find is whether the velocity field satisfy the Navier-Stokes equation. So we need to check for in the 3 direction and arrive at the answer. So in the x direction, the equation is as follows. I am just hurrying up because time is about to be over. But if you have any doubts, you can ask. But yeah, so x direction equation is this: u is equal to 0. So substituting everything everywhere, u becomes 0. So LHS becomes 0, and this also becomes 0. And dou p by dou x actually again again it is a 0 because P is a function of y and z, so this also becomes 0. So x direction it becomes 0. Y direction equation is this, and we are substituting everything. P is equal to minus 2 rho y square minus 2 rho z square. As I mentioned, it is a function of y and z. So dou p by dou y becomes minus 4 rho, and v is equal to minus 2y. So rho into minus 2y, that is sorry, where is my cursor? Yeah. U is 0 and v is minus 2y. Dou v by dou y is minus 2. So here it becomes rho into v, that is minus 2y into 2, equal to minus 4 rho y, that is coming from dou p by dou y, plus this becomes dou square v by dou x square, dou square okay, here velocity viscosity is constant. Okay, dou v by dou y is minus 2, dou square v by dou y square is 0 actually. So again these terms become 0, and we are neglecting gravity. So u is constant, so this also becomes 0. So it is again minus 4 rho y equal to minus 4 rho y plus 0. So again it is satisfied. Now we are writing it in the z direction. So z direction it is given by rho into u into dou w by dou x plus v into dou w by dou y plus w into dou w by dou z equal to minus dou p by dou z plus mu into dou square w by dou x square plus dou square w by dou y square plus dou square w by dou z square plus rho g z. Again this is w equal to 2z. So rho into dou w by dou z will be 2. Dou square w by dou z square will be 0. So the apart from this everything becomes 0, and here apart from this everything becomes 0. So w is 2z into 2 equal to 4 rho z. So again dou p by dou z will be minus 4 rho z. So minus minus it becomes cancelled, becomes plus. So 4 rho z plus 4 rho z, again this equation is satisfied. So Navier-Stokes equation is satisfied. So that was asked in the question, and we can say that Navier-Stokes equation is satisfied. That is for question 14. In question 15, again last question for today's session. So kindly bear with me. It will take 2-3 minutes only, because it is similar to the first problem we saw. A constant thickness film of viscous liquid flows in laminar motion down a plate inclined at an angle theta as shown in figure 4. So this is figure 4. Similar to how in the question 1, this problem is same, except the velocity profile is given by u equal to c into yh cube minus y square h square, and v and w components are 0. So now we are asked to find the constant c in terms of density rho and viscosity mu and angle theta. So same problem, just that u function is varying. So option A, rho g sin theta by mu into 4yh minus h cube. Option B, minus h square rho u sin theta by 2g. Option B, minus h rho g cos theta by 2 mu. Option D, 2h mu sin theta by rho g. Option E, 2 mu rho g by h sin theta. So answer is option A, rho g sin theta by mu 4yh minus h cube. So problem is not a different problem, just that u is a different thing. Other than that everything else is the same. So we just see how to do. So given it is a constant thickness film of viscous liquid flowing in a laminar motion down the plate at an angle theta, which is inclined at an angle theta, and velocity profile is given by u is equal to c into y h cube minus y square h square, and v and w are 0. We are asked to find constant c in terms of rho, theta and viscosity. The solution, continuity equation first we will be writing, and we will be solving for that and checking whether it is satisfying. So dou u by dou x is 0 because u here is a function of y, and v and w are already 0, so continuity equation is satisfied. And next we have to solve for the Navier-Stokes equation, which we will see in the next slide. So assumption, we are seeing steady state, and for thin film flow, as we have seen that pressure along the x direction is usually atmospheric or constant, and there is no flow due to pressure gradient. So here u is a function of y, u is equal to c into y h cube minus y square h square. So continuity equation is verified, which we saw last slide. Now we have to solve for the x direction momentum conservation equation. So rho into du by dt is equal to minus dou p by dou x plus mu into dou square u by dou x square plus dou square u by dou y square plus dou square u by dou z square plus rho gx. So dou u by dou y is equal to c into h cube minus 2yh square. Dou square u by dou y square is equal to c. Okay, this becomes 0. It won't be my h cube. Becomes 0. I mean h cube is a constant, so it becomes 0. So it will be minus 4h minus, okay, h cube will become 0 and it will be minus 2h square. Answer is wrong. Minus 2h square. I derived it with respect to h, but it is minus 2h square. So resolving g vector, we will be getting gx is equal to g sine theta. So we are substituting back in the equation. So it is mu into dou square u by dou y square. So it is mu into minus 2h square plus rho g sine theta. So which becomes rho g sine theta will take that side, and we will actually take mu c 2y square to the other side. So this becomes plus. So c is equal to rho g sine theta by mu into 2h square. This is wrong actually. 2h square. So this is the right answer actually. C is equal to rho g sine theta by mu into 2h square. So we have to change option as well. This is wrong. So yeah, this is, so yeah, answer is option A, rho g sine theta by mu 2h square. So this is similar to the problem that we solved first, that is question 1. So same problem, might be different numerics, that's it. So yeah, I mean time got extended by some minutes, and I'll check. One more thing is, I'll just check that pressure gradient problem once again, and if there is any change, I'll be making that change and uploading it. While uploading it, I'll make the proper thing. So just check that once before assignment submissions if you have any doubts. So yeah, that's it for today's class. If you have any doubts in any of these problems, you can ask. We can discuss. Time got extended by 9 minutes. Sorry for that. If you have any doubts, you can ask, or else that's it for today's session. Or else any other doubts also you can ask if you have. The pressure gradient sum alone, I'll check once and I'll upload the correct one when I'm uploading the PDF. I mean, presentation will also be given to you and video links also will be given. So yeah, that's for today's session. For a question in the assignment, which question? I mean, if you're having any difficulty, I can help you. Which question exactly? Options, it wasn't there. Okay. Maybe you can post in the forum if that is the case. Because I didn't solve the assignment problems actually. I'll also check the assignment problem. But yeah, for if you're having any issues with respect to not finding the answers from the assignment, I mean not finding the answers in the options, you can access the that NPTEL forum and post your doubts there with respect to the original assignment question. Yeah, okay. Thank you then. I'll stop the recording first.